In Chapter 6, Section 1, we'll learn about normal probability distributions, and we'll start with the standard normal distribution. Recall that a normal distribution, or sometimes called the bell curve, is a distribution that occurs naturally in many situations. For example, the bell curve can be seen in some test scores where the bulk of students will earn an average score of a C, while a smaller number of students will earn a score of a B or a D, and even smaller number of students will score an F or an A. This creates a distribution that resembles a bell. The bell curve is symmetrical, and half of the data will fall to the left of the mean of the curve, and half of the data will fall to the right of the mean of the curve. In this section, we will learn about a specific normal distribution known as the standard normal distribution. The standard normal distribution is a normal distribution, but it has a mean of 0 and a standard deviation of 1. The standard normal distribution is a specific normal distribution having the following three properties. The graph of the standard normal distribution is bell-shaped. The standard normal distribution has a mean equal to 0, and the standard normal distribution has a standard deviation equal to 1. In this section, we will develop the skills to find areas or probabilities corresponding to various regions under the graph of the standard normal distribution. In addition, we will find z-scores that correspond to the areas under the graph. If a continuous random variable has a distribution with a graph that is symmetric and bell-shaped, we say that it is a normal distribution. Here is the formula for a normal distribution. For this class, for Stat 251, you won't be using this formula to calculate or to graph any normal distributions. If you were to plot the formula of the normal distribution, you will get a density curve that looks like the one displayed here, with a mean of mu and a standard deviation of sigma. The density curve is symmetrical, centered about its mean, and its spread is determined by the standard deviation. The height of a normal density curve is at a given point x is given by the normal distribution formula. While the focus of this chapter is the normal probability distribution, we will first look at the uniform distribution. A continuous random variable has a uniform distribution if its values are spread evenly over the range of possibilities. The graph of a uniform distribution results in a rectangular shape. The properties of the uniform distribution include, first, the area under the graph of a continuous probability distribution is equal to 1. And second, there is a correspondence between the area and probability, so that probabilities can be found by identifying the corresponding areas in the graph using this formula for the area of a rectangle, where area equals to height times width. Both the normal distribution and the uniform distribution are known as density curves. The graph of any continuous probability distribution is called a density curve, and any density curve must satisfy the requirements that the total area under the curve is exactly 1. Because the total area under any density curve is equal to 1, there is a correspondence between area and probability. Let's consider this example. During certain time periods at JFK Airport in New York City, passengers arriving at the security checkpoint may have waiting times that are uniformly distributed between 0 minutes and 5 minutes, as we will see on our next slide. Recall the properties of a uniform distribution. First, the area under the graph is a continuous probability distribution that is equal to 1. there is a correspondence between area and probability, so that probabilities can be found by identifying the corresponding areas in the graph using the formula of a rectangle where area equals to base times height. Also, as the uniform distribution here displays, all of the different possible waiting times are equally likely to occur. Waiting times can be any value between 0 minutes and 5 minutes, so it's possible to have a waiting time of, let's say, 1.23456 minutes. By assigning the probability of 0.2 to the height of the vertical line in this figure, the enclosed area is equal to 1. In general, we should make the height of the vertical line in a uniform distribution equal to 1 over the range. In this example, our range is the maximum value minus the minimum value, or 5 minus 0. And 1 over 5 minus 0 is equal to 0.2. Given the formula distribution illustrated in the figure, let's find the probability that a randomly selected passenger has a waiting time of at least 2 minutes. The shaded area represents the waiting times of at least 2 minutes. Because the total area under the density curve is equal to 1, there is a correspondence between area and probability. So we can easily find the desired probability by using area. So we want to find the probability of having a wait time of at least 2 minutes. So we would say the probability of a wait time of at least 2 minutes is equal to the height times the width of the shaded area in our figure. And so that is equal to 0.2, which is the height, times 3, which is our range, because we're going from 2 to 5, so 5 minus 2 equals 3, so that's our range. And that is equal to 0.6. So we can say that the probability of randomly selecting a passenger with a waiting time of at least 2 minutes is 0.6. Let's review the standard normal distribution. Because the density curve of a normal distribution has a more complicated bell shape, it's more difficult to find areas. However, a basic principle of probability distributions is that there is a correspondence between area under the curve and probability. The normal distribution displayed here is the standard normal distribution. The area under this density curve is equal to 1, and we will use z-scores as a label for the x-axis, or the horizontal axis. We can define the standard normal distribution as follows. The standard normal distribution is a normal distribution with the parameters mu equals to 0 and sigma equals to 1. The total area under the density curve is equal to 1. We can find areas or probabilities for different regions under a normal model using technology or Table A2 in our appendix. However, using calculators and softwares generally give you more accurate results than Table A2, so it is strongly recommended to use technology when possible. If using Table A2 in our appendix, it's essential to understand these points. First, Table A2 is designed only for the standard normal distribution, which has a normal distribution with a mean of 0 and a standard deviation of 1. Second, Table A2 is on 2 pages, with the left page giving the negative z-scores and the right page giving the positive z-scores. Each value in the body of the table is a cumulative area from the left up to the vertical boundary above the specific z-score. And also, when working with a graph, avoid confusion between z-scores and areas. Z-scores are the distance along the horizontal scale, or the x-axis, of the standard normal distribution, and they correspond to the number of standard deviations either above the mean or below the mean. The area is the region under the curve, and it refers to the value in the body of the table A2. And finally, the part of the z-score denoting the hundredths is found across the top row of table A2. The z-score table can be found in the back of the book on pages 560 and 561 of this textbook, but I will also post copies of the z-score table in the Chapter 6 module. As mentioned previously, we can use either the z-score table or technology to find the probabilities when given specific z-scores. We will go over a couple of examples to find probabilities using both the table and as well as technology. Let's consider this example. A bone mineral density test can be helpful in identifying the presence or likelihood of osteoporosis. The results of a bone density test is commonly measured as a z-score. The population of z-scores is normally distributed with a mean of 0 and a standard deviation of 1. So these test results meet the requirements of the standard normal distribution. Here we have the graph of the bone density test scores. Let's say a randomly selected adult undergoes a bone density test. Let's find the probability that this person has a bone density test that is less than 1.27, or the probability that Z is less than 1.27. Note that the probability that Z is less than 1.27 is equal to the green shaded area under the curve. So we need to find the probability that Z is less than 1.27, which again is the shaded area under the curve, and to the left of Z equals to 1.27. Using table A2, begin with the z-score of 1.27, and we will find it by locating 1.2 in the left column of our table, and in this case we're using our positive table. So once you have found 1.2 in your left column, then you find the adjoining row of the probabilities that is found in the column labeled 0.7. And you can see highlighted in red is our probability. Table A2 shows that there is an area of 0.8980 that corresponds to the z-score of 1.27. We want the area below 1.27, and the area in table A2 gives us the cumulative area from the left. So the desired area in this example is 0.8980. Because of the correspondence between area and probability, we know that the probability of a z-score below 1.27 is equal to 0.8980. Let's interpret our findings. The probability that a randomly selected person has a bone density test result that is below 1.27 is 0.8980, shown in the shaded region. Another way to interpret this result is to conclude that 89.8% of people have a bone density test level that is below 1.27. Let's consider another example of our bone density test. This time we will find the area to the right of a z-value. So using the same bone density test, find the probability that a randomly selected person has a result above -1.0. which is considered to be the normal range of a bone density test reading. In other words, let's find the probability that z is greater than negative 1.0. Because our z-score is negative, we will use the negative z-score side of the standard normal distribution table. If we use table A2, we need to be aware that it is designed to apply only to cumulative areas from the left up to the z-score value. So referring to the page with the negative z-scores, we find that the cumulative area from the left up to z equals to negative 1 is equal to 0.1587. In this graph, that is the white area under our curve, but what we are interested in is the green color, the green shaded area under our curve. Recall that the total area under the curve is 1, so we can find that green shaded area by simply subtracting 0.1587 from 1, and the result is 0.8413. So the area under the green shaded part of our curve is 0.8413. Let's interpret our findings. Because of the correspondence between probability and area, we can conclude that the probability of randomly selecting someone with a bone density reading above -1 is 0.8413. This is the same as the area above the right of the -1. So we could say that 84.13% of the people have a bone density level that is above -1. Let's consider another example using our bone density test, but this time we will find the area between two z-values. A bone density test between -1 and -2.5 indicates the subject has osteopenia, which is some bone loss. Let's find the probability that a randomly selected subject has a reading between -1 and -2.5, or that the probability of -2.5 is less than z is less than -1. The first thing we want to do to find the area or the probability that z is between -1 and -2.5 is to first find the area where z is equal to -1. And we found that in our previous example. So the area to the left of z, where z equals to -1, is equal to 0.1587. Next, we want to find the area to the left of z equals to -0.25, and that is equal to 0.0062. So the area between z equals to -1 and z equals to -2.5 is the difference between the two areas we just found above. So we can say that the probability of -2.5 is less than z is less than -1 is equal to 0.1587 minus 0.0062, which is equal to 0.1525. Using the correspondence between probability and area, we can conclude that there is a probability of 0.1525 that a randomly selected subject has a bone density reading between -1 and -2.5. Another way to interpret this result is to state that 15.25% of people have osteopenia with a bone density reading between -1 and -2.5. The generalized rule states that the area corresponding to the region between two z-scores can be found by finding the difference between the two areas found in our table A2. It isn't necessary to memorize the rule of the formula. Instead, Focus on understanding the rule by using a graph. Draw a graph, shade the desired area, and then think of a way to find that desired area by working with the cumulative areas from the left. Let's review some notation. The probability of A less than Z less than B denotes the probability that the Z-score is between the values of A and B. The probability that Z is greater than A denotes the probability that the Z-score is greater than A. And the probability of Z less than A denotes the probability that the Z-score is less than the value of A. Now let's consider how we might find a Z-score given that we know the area. The first thing is to draw a bell-shaped curve and identify the region under the curve that corresponds to the given probability or to the known area. If that region is not a cumulative region from the left, work instead with the known region that is a cumulative region from the left. Second, use technology or table A2 to find the Z-score. With table A2, use the cumulative area from the left, locate the closest probability in the body of the table, and identify the corresponding Z-score. For the standard normal distribution, a critical value is a Z-score that is on the borderline separating those Z-scores that are significantly low or significantly high. The expression Z subscript alpha denotes the Z-score that corresponds to the area of alpha that is to its right. Let's find the value of Z subscript alpha where alpha equals to 0.025. The notation Z subscript 0.025 is used to represent the Z-score with an area of 0.025 that is to the right of that Z-score. Using table A2, one way we can find the value of Z subscript 0.025 is as follows. First, we find the Z-score using the positive side of the table A2 that corresponds to the area of 1 minus 0.025, and that equals to the area of 0.975. So the area that corresponds so the Z-score that corresponds to that area of 0.975 is equal to 1.96. So refer to the graph below and note that the value of Z equals to 1.96 has an area of 0.025 to its right. So we can say that Z subscript 0.025 is equal to 1.96. When finding a value of Z subscript alpha for a particular value of alpha, note that alpha is the area to the right of that Z value, Z subscript alpha. But table A2 and some technologies will give you the cumulative areas to the left of a given Z-score. To find the Z value of Z alpha, resolve that conflict by using the value of 1 minus alpha. For example, to find the value of Z subscript 0.1, refer to the Z-score that corresponds to the area of 0.9 to the left of that Z-score. This is the end of Chapter 6, Section 1. Please proceed to Chapter 6, Section 2.